Every wind power setup you have ever encountered suffers from the same limitation. It depends on wind. Not merely any breeze, but wind that is steady, powerful, and moving in a predictable direction, the kind that consistently reaches 12 miles per hour, 19 kilometers per hour, or higher, exactly where the turbine is positioned and at the elevation of its tower. The reality is that most of the United States does not experience those conditions. Most residential properties do not experience those conditions. For most locations and most hours of the year, wind is weak, chaotic, constantly shifting, and largely ineffective for a conventional horizontal axis turbine mounted in a backyard. What follows is a different approach. This system uses a wind funnel, a concentrating duct structure engineered to capture slow, dispersed, multidirectional airflow available at only 3 miles per hour, 4.8 kilometers per hour. That level of wind exists in nearly every location almost all the time. The duct accelerates that airflow until it reaches the velocity required to operate a generator, using approximately $90 worth of materials that can be purchased from a hardware store or farm supply outlet. The science responsible for this effect is known as the Venturi effect. It is the same phenomenon that causes water from a garden hose to exit faster when a thumb partially blocks the opening. This concept is neither experimental nor recent. Wind concentration systems based on this principle have been examined by institutions, including the University of Auckland and the Technion Israel Institute of Technology. Published findings from these studies reported power production increases ranging from 2 times to 5 times compared with a comparable open-air turbine operating under identical wind conditions. To understand why this design functions and why many residential wind turbines fail to meet expectations, only a brief explanation of wind power physics is necessary. One number matters above all others. The energy contained in moving air is proportional to the cube of wind speed, not the square, the cube. Because of this relationship, even small increases in velocity create very large increases in available energy. If wind speed rises from 6 miles per hour, 9.7 kilometers per hour, to 12 miles per hour, 19.3 kilometers per hour, the available power grows by 2 cubed. That equals 8. Twice the wind speed produces 8 times the available power. A system capable of increasing airflow from 3 miles per hour, 4.8 kilometers per hour, to 6 miles per hour, 9.7 kilometers per hour, delivers 8 times more energy to the turbine than the original airflow could provide. 8 times more power resulting solely from a change in geometry. That principle forms the entire foundation of wind concentration technology. No additional wind is being created. The system simply increases the velocity of existing airflow through duct design. Since available power rises with the cube of velocity, even modest acceleration can generate substantial gains. The Venturi effect provides the mechanism behind this process. When a fluid, including air, moves through a narrowed section, it must speed up to preserve flow continuity. The same quantity of air that travels slowly through a wide passage is forced to move more rapidly through a restricted one. A converging duct begins with a large opening and gradually narrows toward the turbine location. This shape accelerates incoming air before it reaches the rotor. A diverging section positioned after the turbine widens toward the exit. This expansion creates a lower pressure region around the turbine and pulls additional air into the system from outside the inlet area. Combining a converging entrance with a diverging exit while placing the turbine at the throat produces a configuration that maximizes both velocity enhancement and effective collection area. Professor David Sharp published theoretical research on diffuser-augmented wind turbines, the engineering term for this type of arrangement. His analysis indicated that the theoretical power coefficient of a ducted turbine can exceed the Betz limit. The Betz limit, equal to 59.3% of available wind energy, represents the maximum theoretical efficiency of an unducted rotor. A properly engineered duct attracts airflow from beyond the direct stream entering the rotor. In effect, it increases the capture area beyond the physical diameter of the turbine itself. For this reason, the Betz limit does not apply in the same manner. At the University of Auckland, Professor Grant and his research group constructed and evaluated physical diffuser-augmented wind turbine prototypes. Their testing showed power generation reaching 4.5 times that of the identical rotor operating without a duct under the same wind conditions. 4.5 times greater output at the same wind speed, achieved solely through a change in geometry. The system described here is a residential do-it-yourself adaptation of that principle. It is not a precision aerospace assembly. Instead, it is a correctly proportioned duct structure built from plywood, sheet metal, and standard hardware. The design captures the acceleration effect and directs it toward a small commercially available turbine or generator while costing only a fraction of most commercial small wind systems. Every component uses real specifications and actual pricing in US dollars with equivalent international costs where appropriate. The first material is exterior grade plywood with a thickness of 12 millimeter. 2 sheets measuring 4 by 8 foot or 1.2 by 2.4 meter, are required. These panels form the primary structure of the duct walls. Exterior grade material is necessary because the unit will remain exposed to weather conditions. Cost ranges from $18 to $24 per sheet, bringing the total to $36 through $48. The second component is a small permanent magnet DC generator or a stepper motor, repurposed as a generator. It should be rated for 12 volts and produce at least 100 watts at 600 RPM. Generators of this category are commonly available from online suppliers for $15 to $25. Another option is a treadmill motor obtained from sports equipment recyclers for $10 to $20. These motors function effectively because they are permanent magnet DC units capable of generating clean DC voltage when the shaft rotates. The third item is a set of 3 rotor blades. These can be carved from white pine lumber. One board measuring 2 by 6 inch, 5 by 5 centimeter, and 8 foot, or 2.4 meter in length, provides enough material for 3 functional blades at a cost of roughly $3 to $4 total. Alternatively, a pre-manufactured 3-blade rotor kit designed for small wind turbines can be purchased from online suppliers for $15 to $20. The fourth component is a sheet of 26-gauge galvanized metal measuring 3 by 8 foot, or 0.9 by 2.4 meter. The sheet forms the inner curved surface of the duct throat and costs $6 to $10 at any sheet metal or HVAC supply. Additional supplies include exterior wood screws, wood glue, waterproof sealant, and mounting hardware, totaling $8 to $12. A 12-volt charge controller rated for 10 amps minimum regulates output from the generator to a battery bank and prevents overcharging, priced $8 to $15. Total system cost using U.S. retail pricing ranges from $90 to $115. With low-cost sourcing, including a used treadmill motor, homemade blades, and clearance plywood, the build can be completed for $65 to $75. The duct's geometry defines the system. Correct proportions ensure the physics functions properly. Errors in taper angle, throat diameter, or expansion ratio generate turbulence that diminishes rather than increases performance. The exact dimensions that produce effective acceleration without causing flow separation are as follows. Flow separation occurs when accelerated air detaches from duct walls, producing drag instead of smooth flow. The inlet is 48 inches wide by 48 inches tall, 122 centimeter by 122 centimeter, forming the capture area that intercepts incoming wind. This size is the minimum for the rotor. The throat holding the rotor is 24 inches in diameter, 61 centimeter. The inlet area equals 2,348 square inches, 14,864 square centimeter. The throat area is approximately 452 square inches, 2,916 square centimeter, creating an area ratio of roughly 5.1 to 1. Accounting for wall friction and minor flow separation, the effective velocity increase ranges from 2.5 to 3.5 times, delivering a power increase of 15 to 43 times compared to the same rotor in open air. Even the lower end is transformative for low wind speed energy capture. The diffuser expands from 24 inches, 61 centimeter at the throat, to 36 inches, 91 centimeter at the outlet over 24 inches, 61 centimeter of length. Diffuser wall half angle is 14 degrees. This angle is critical. Below 7 degrees, the diffuser is too gradual to produce meaningful low pressure. Above 15 degrees, flow separation occurs and turbulence cancels the advantage. 14 degrees represents the optimal range. The converging inlet extends 24 inches, 61 centimeter from the 48-inch, 122 centimeter square inlet to the 24-inch, 61 centimeter circular throat. This length allows air to accelerate smoothly without abrupt velocity changes that cause turbulence. Total duct length is 48 inches, 122 centimeter, consisting of 24 inches, 61 centimeter of converging inlet, and 24 inches, 61 centimeter of diverging diffuser with no parallel throat section. This compact design can mount on a standard roof ridge or garden post. Assembly begins with cutting panels. 4 trapezoidal inlet side panels measure 48 inches, 122 centimeter at the front, and 24 inches, 61 centimeter at the back, 24 inches, 61 centimeter long. This trapezoid creates the converging inlet when assembled into a squared around box. Cut all panels from the first plywood sheet using a circular saw and straight edge guide. Assemble with exterior screws and waterproof wood glue along every joint. The front face is 48 inches square, 122 centimeter square, and the back face is circular connecting to the throat. Use galvanized sheet metal to form and rivet a smooth curved transition ring at the throat, directing airflow from the converging inlet into the circular throat and preventing flow separation. The rotor plate is a circular plywood disc 24 inches, 61 centimeter in diameter, and 18 millimeter thick, with a central hub bearing housing for the generator shaft. It mounts at the throat junction where the inlet ends and diffuser begins. Center the generator so the shaft protrudes forward through the bearing. Attach 3 blades to a hub on the shaft with 15 to 20 degrees tip pitch and 30 to 35 degrees root pitch, standard for low wind speed rotors. The diffuser consists of 4 rectangular plywood panels, each 24 inches, 61 centimeter long, angled outward at 14 degrees from the center line. Assemble them into the expanding section mounting to the back of the rotor plate, expanding from 24 inches, 61 centimeter at the throat to 36 inches, 91 centimeter at the outlet over 24 inches, 61 centimeter of length. Apply 2 coats of exterior paint or weatherproof sealant to all plywood surfaces before assembly, focusing on sealing all end grains, which wick moisture and can delaminate panels within 2 to 3 seasons if left untreated. Mount the complete duct assembly on a pivot so the inlet face tracks wind direction. A simple lazy Susan bearing on a post or roof ridge allows passive wind tracking. A tail vane, a flat plywood fin on an arm behind the diffuser outlet, keeps the inlet oriented into the wind automatically without electronics. Connected generator output wires to the charge controller and the controller output to a 12-volt battery bank. This completes the electrical circuit. No inverters, grid tie, or permits are required for standalone DC charging in most U.S. jurisdictions. A 3-phase permanent magnet generator produces raw AC, requiring a bridge rectifier, a 4-diode module under $2, to convert to DC before the charge controller. If a DC treadmill motor is used, the output is already DC and connects directly to the charge controller without a rectifier. A fully charged 100 amp-hour 12-volt battery bank stores 1,200 W-hours. At the power levels, this system generates in 6 to 8 ampere, 9.7 to 12.9 kilometer per hour wind, 15 to 40 watts continuous, that battery charges in 30 to 80 hours of wind operation. Use local average annual wind speed data from the National Renewable Energy Laboratory, wind resource maps, freely available online. Enter your zip code to find average wind speeds at various heights. At 3 mph, 4.8 km per hour, the system's rated startup speed, output is modest. At 6 mph, 9.7 km per hour, typical across most of the continental United States, the system produces meaningful continuous charging that supports small off-grid loads. At 3 amp, 4.8 km per hour inlet wind, the duct accelerates air to about 7.5 to 10.5 MF, 12 to 16.9 km per hour at the rotor. Power from a properly built 24-inch, 61 centimeter diameter rotor at this speed is 3 to 8 watts. This is sufficient to trickle charge a 12-volt battery or run a USB charging circuit. At 6 amp, 9.7 km per hour inlet wind, rotor speed is approximately 15 to 21 MEPS, 24.1 to 33.8 km per hour at the throat. Power output ranges from 20 to 55 watts, enough for full evening LED lighting, phone and device charging, and small radio or communication equipment. At 10 mph, 16.1 km per hour inlet wind, rotor speed at the throat is roughly 25 to 35 feet, 40.2 to 56.3 km per hour. Power output reaches 90 to 180 watts, allowing laptop operation, a 12-volt refrigerator on a duty cycle, or maintaining a battery bank for overnight LED lighting and morning device charging without grid input. This system does not supply a conventional home's full load and does not compete with a 5 kilowatt solar array. A 24-inch, 61 centimeter rotor has a power ceiling defined by its swept area. The $90 windfunnel is a serious off-grid supplement and an effective low wind speed energy source, but not a whole home solution. Standard 400-watt small wind turbines generate significant power at 7 to 9 mph, 11.3 to 14.5 km per hour, reaching rated power only at 28 mph, 45 km per hour or higher. The wind funnel begins producing usable energy at 3 mph, 4.8 km per hour, a speed present almost everywhere continuously, including sites that conventional maps classify as unsuitable for turbine installation. Placement determines performance more than construction details. The inlet face must be elevated at least 10 feet, 3 meter, above nearby obstructions. Ground level wind is slow and turbulent due to friction with the surface and obstacles. At 30 feet, 9.1 meter, wind is typically 40 to 60% faster than at 6 feet, 1.8 meter, and much smoother. Even raising the system from 6 feet, 1.8 meter to 20 feet, 6.1 meter, doubles average power more reliably than duct geometry improvements. Avoid locations downwind of buildings, trees, or terrain at a minimum distance of 10 times the obstruction height. A 30-foot, 9.1 meter tree produces turbulence for 300 feet, 91.4 meter downwind. Turbulent wind enters the duct at random angles, stalls the rotor, and delivers far less power than clean laminar wind at the same average speed. The tail vane passive tracking functions in winds above roughly 4 amp, 6.4 km per hour. Below this, manual orientation toward prevailing winds is most effective. Seasonal adjustments may be necessary as local prevailing wind direction often shifts between winter and summer. 4 construction errors account for most underperforming builds. First, an incorrect diffuser angle. The 14-degree half angle is essential. Steeper angles produce flow separation, turbulence, and a wake behind the rotor instead of the intended low-pressure zone. Use a protractor and measure carefully. Second, poor rotor blade pitch. Blades less than 10 degrees stall in low wind. Blades over 40 degrees produce drag, acting like paddles instead of airfoils. 15 to 20 degree tip pitch and 30 to 35 degree root pitch is correct for low wind operation. Third, incorrect rotor mounting. The rotor must sit at the throat, the junction of the converging inlet and diverging diffuser. Mounting it forward 4 to 5 inches, 10 to 12.7 centimeter, puts it in accelerating flow before maximum speed. Mounting behind places it in decelerating flow. Throat position is the only correct placement for maximum power. Fourth, leaving plywood end grains exposed. While performance is unaffected initially, unsealed plywood fails in 2 seasons. Seal every edge, cut, and hole with exterior paint or sealant. Delaminated panels in the diffuser disrupt smooth airflow essential to the diffuser geometry. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.